One application of differential equations is to determine the function to a situation with lines or curves in the coordinate plane. This video discusses the procedure with examples using straight lines. In order to identify a certain equation for different trending lines or curves in a situation, elimination of arbitrary constants is integrated to identify the differential equation. For start, one has to identify the proper equation to be used in the given situation. In case of problems requiring a straight line crossing a given point, the solution to start from is y minus y1 is equal to m times x minus x1. For a straight line using the slope, y is equal to mx plus b can be used. A circle with center at a given point, the solution comes from x minus h squared plus y minus k squared is equal to r squared, where horizontal parabola takes the function y squared is equal to 4ax, and vertical parabola will work with x squared is equal to 4ay. These are just few standard functions for different curves which one is expected to understand from analytic geometry. Example number 1. Determine the differential equation for straight lines passing through the origin. For a straight line and a point, the formula to be integrated is y minus y1 is equal to m times x minus x1, where x1 and y1 will be taken as 0 as the problem states that the line passes through the origin. The formula is then simplified as y is equal to m times x, and this simplified formula shows a single constant m, which denotes one derivation. So derive the function giving y prime is equal to m, and since the derived function still contains the constant, use substitution to eliminate the arbitrary constant, whereby the first and second equations are to be identified. Plug equation 2 into 1 and get y is equal to x times y prime, which is the required differential equation, or this can then be replaced in the dy all over dx form to get y dx minus x dy is equal to 0. Example number 2. Determine the differential equation for straight lines passing through a fixed point. The coordinates are parameters. Still with a specified point used, the equation would be y minus y1 is equal to m times x minus x1, where we can simplify y1 as k and x1 as h, then check that they are parameters, thus the only constant in the function is m, which says that we should derive once. If we isolate m to easily cancel it out later, we get m is equal to y minus k all over x minus h, and the function requires quotient rule. In deriving, take the square of the denominator and apply low d high and high d low, so that would be x minus h times the derivative of the numerator, which is y prime, minus the numerator y minus k times the derivative of x minus h, which is 1. The fraction is equated to the derivative of the constant m, which is 0. The simplified dE is then given as y prime times x minus h minus y minus k is equal to 0. Or in the other form, we would arrive at x minus h dy minus y minus k dx is equal to 0. In case we are to use implicit differentiation instead of quotient rule, we derive y, which is 1 times dy, minus the derivative of k, which is then 0, and this is equal to m times the derivative of x, which is 1 times dx, minus the derivative of h, which is 0. The function can then be simplified as dy is equal to m times dx. So isolating m, we have m is equal to dy all over dx. The constant m is still present in the differential equation, so we call it equation 2, and the original function will be equation 1. By substitution of 2 into 1, we get y minus k is equal to dy all over dx of x minus h. Multiply the whole thing by dx to eliminate the denominator to have y minus k times dx is equal to x minus h times dy. And arrange terms to get y minus k dx minus x minus h dy is equal to 0. Example number 3. Determine the differential equation for straight lines with slope and y-intercept equal. With the requirement of the slope in this situation, the formula for the line will be y is equal to mx plus b, where the slope m will be equal to the y-intercept b. And substituting the condition, we get y is equal to mx plus m. It is noted that there is one arbitrary constant saying we can derive once. So simplify the equation and derive, but take note that it needs to employ the quotient rule. So use low d high and high d low all over the square of the denominator. That would be x plus 1 times y prime minus y times 1 all over the square of x plus 1. And cross the denominator with 0 to eliminate it. So by expanding the terms, the differential equation is then found out to be y prime times x plus 1 minus y is equal to 0. By using dy all over dx to replace y prime, we get x plus 1 dy minus y dx is equal to 0. Example number 4. Determine the differential equation for straight lines with slope and x-intercept equal. With y is equal to mx plus b, we know that b is the y-intercept, but the condition requires x-intercept. So we equate y to 0. mx is equal to negative b, and x is then found out to be negative b all over m. Then the condition states that the slope is equal to x. So we get m is equal to negative b all over m, which is then simplified as b is equal to negative m squared. Plug b into the original equation to have y is equal to mx minus m squared. So in the resulting formula, there is one constant requiring one derivation. If we derive, we get y prime is equal to m times 1 minus 0, which is simplified as y prime is equal to m. And until this point, m is still present, which would require some substitution. So take y prime as equation 2 with the original equation as the first, and plug them together to have y is equal to y prime x minus y prime squared. Then arrange the terms to get y prime squared minus xy prime plus y is equal to 0. Example number 5. Determine the differential equation for straight lines with algebraic sum of the intercepts fixed as k. With y is equal to mx plus b and the condition, we look for x-intercept by equating y to 0. So again, we have x is equal to negative b all over m. And the condition states that x and y intercepts when added will be k. So we have b plus negative b all over m is equal to k. And simplifying this, we arrive at b times m minus 1 is equal to m times k. Now isolate b to have b is equal to m times k all over m minus 1. This formula for b is then plugged into the original equation. Thus we have y is equal to m times x plus m times k all over m minus 1. And in this function, m is the notable constant, denoting that we should derive once. Y prime turns out to be m times 1 plus 0, as the whole second term is a constant, and the presence of the constant m would make y prime function will be equation 2 and y function will be equation 1. Plug function 2 into 1 to get y is equal to y prime times x plus y prime times k all over y prime minus 1. And arrange terms, then eliminate the denominator to have y prime times x minus y times y prime minus 1 plus y prime times k is equal to 0.